Hello everyone. Thank you for watching this video. Today I'm going to present our work, a new optics-based physical world adversarial attack that exploits only one of the most common natural phenomena, shadow. It's well known that machine learning models are vulnerable to adversarial attacks. Existing works on adversarial examples are either in the digital domain, where the perturbations are directly added to the inputs of a model, or in the physical world, where perturbations are physically added to the objects themselves. One popular approach for physical world attacks is to adopt the sticker pasting strategy, where the adversarial patterns are printed as stickers and then attached onto the target object, for example, a road sign. This is an effective way. However, it's invasive and it's not always possible to access the target object. Recently, a new type of attacks try to cast perturbations by optics-based tools. This is a good idea since it's non-invasive, making attacks more flexible and stealthier. However, all existing methods require sophisticated man-made equipment like a projector. So here is a question. Can common optical natural phenomena like shadows result in adversarial effects? Our answer is yes. All we need to do is place the light-blocking object such as a cardboard in the right place to produce an appropriate shadow, then we can fool the classifier to give a wrong prediction. As you can see in the video on the right, a speed limit 25 sign is consistently recognized as a speed limit 35 sign. This attack method is obviously non-invasive, and at the same time, by making use of shadows, no sophisticated man-made equipment is needed. To simulate shadows in a digital image, we need a binary mask M to constrain the shadow areas, a set of vertices V which determines a polygonal shadow area PV, and a coefficient K used to control the brightness of the shadow area. Since the L channel in lab color space can be used to effectively model the shadows in the real world, we can simulate shadows by simply multiplying the corresponding L channel with coefficient K. Given the original image X, the binary mask M, and the shadow coefficient K, our objective is to figure out the optimal shadow area, which is equivalent to figure out a set of vertices V such that the confidence of the classifier on the ground truth class can be minimized. However, there are discrete coordinates values and a Boolean function in our object, making it hard to solve by gradient-based methods. Therefore, we apply heuristic search techniques instead, such as particle swarm optimization, so that a valid solution can be found quickly without the help of gradients. For physical adversarial examples, their robustness against all kinds of variations caused by a moving camera is an important consideration. A widely used technique to deal with this problem is expectation over transformation, which minimizes the objective on some augmented images generated online. After that, we can further stabilize the output to the wrong class with a targeted objective. Our evaluations on LISA and GTSRB datasets show that our attack is highly successful with high query efficiency, which tells us that even the most common natural phenomenon can pose a real threat to AI security. Due to the angle change of the sunlight, the generated shadow will move over time, which inspires us that our method can be used to conduct an interesting scheduled attack. That is, we can control our shadow perturbation to be harmless in most of the time but to be adversarial at a certain time. For example, the peak traffic hour in the morning. As shown in this video, at around 8:30 and 30 seconds AM, which is our scheduled time, the classifier produces the expected wrong outputs. Meanwhile, at other times, such as 8:32 AM, the outputs of the classifier are correct. One of the most effective defense strategies against adversarial examples is adversarial training, which improves model robustness by using newly generated adversarial examples as training samples in each epoch. We tested it in our setting and found that adding images with random shadows to each training epoch did improve the model's robustness to our attack. Finally, as a new type of attack, there surely would be some drawbacks or limitations. As shown in the figures on the right, as K increases, the attack success rate decreases, and the average number of queries increases, which means that our attack requires a good weather to produce a lower K. To remedy this problem, we can achieve the adversarial effect through a stronger artificial light. Another limitation is that we cannot explicitly conduct targeted attacks, which is probably due to the perturbation directions produced by shadows are relatively single. However, as shown in our experiments, we are able to achieve comparable results to that of targeted attacks in terms of the stability of predictions. In conclusion, we propose a new optics-based attack that exploits only one of the most common natural phenomena, shadows. For code, models, and further information, feel free to contact us through email or visit our project page. Thank you for watching this video.